So this program may be the hardest program that you do. And so conceptually it's difficult and the way that it's written is a little difficult. And so if you get to this point and you feel really good about yourself and you feel like you understand everything, and you get to this program and you don't understand it as much, that's fine. There's a great video that I linked on this page by a video that Ben Eater made that explains this long division in depth, and it is absolutely brilliant. But I had to watch it a couple of times before I fully absorbed it. And it may be worth watching that video a couple of times before you fully absorb what's happening in order to understand what this program is actually doing. So if you need to, just pause the video right now, go watch that other video where it's linked to, and you can see visually what it's going to do. Welcome back. So why are we doing this? As you remember, when we did our integer to ASCII the last time, we did it with bases of 10. And what we had to do is we had to create the biggest base of 10 that could fit within the 32-bit integer and then keep subtracting it, which is great if we're only working with numbers that fit within that space. And so what we're going to do is we're going to take a 64-bit number and do an integer to ASCII conversion on it with 32-bit registers. So you may be thinking, well, we could compare the higher bits and see if they are less than and greater than, and if it's less than, then compare the lower bits. We could do that. But there's another way that we can do it, and this is the way that we can divide numbers not only um, like this, but it's also the way that we can find out like the digits of pi. We can use this method to divide out non-terminating numbers, irrational numbers. And so what we need to do is do long division. Did you know computers could do long division? So let's start, and I'll try and explain some of this as we go. We have our two 32-bit numbers, and what we need to do is we need to multiply them together. And we'll use the umul instruction, the unsigned multiplication. And what we're going to do is we're going to put the high bits in register 5 and the low bits in register 4. And so the way the syntax is that we have the low bits and then the high bits, the destination registers, and then the two numbers that we're multiplying together. And I'm just going to write what this actually does here in the comments. It's R0 times R1, and it equals the high bits in R5 and the low bits in R4. You might as well just start a registers area up here. So we'll say R4 is 64 low, and R5 is 64 high. Just like that. We need to create some kind of link to our output. And we're going to put this in R8, output memory. And again, load register R8 equals output. And now when we do this, unlike last time where we could just write the numbers as we got them, we need to start at the end of the string and write it backwards. And so what we're going to do is now that we have the ending address or the beginning address for this output, we're going to go to the end by adding 20. Because 20 is the max length plus the line ending. So since there's a 0 index, adding 20 will get us to the last bit of memory that's reserved. And then we're going to put our line ending first. And so we're just going to use R7 for now. It's not that important because we haven't actually gotten to the program yet, and if this gets overridden, it's not a big deal. Store byte, and we're going to put this value, R7, into the address at R8. And all the other times we've been using 1, but now that we're at the end, we're going to use -1 to decrement the address after the write. So what do we need? We need to shift both registers together. We need to make sure we're not losing any information. And we need to create a register that holds the number that we're going to try and subtract 10 from. And so let's create the register that we're going to try and subtract 10 from first. We'll use register 6, and we'll just call this our working number. And then we need to take the number that we receive and assign it to an ASCII code. And we'll just use R7 for that. The last thing that we need, and I think it's the only other thing that we need, is we need a loop counter. When we do the shifting, we want to do it only the exact amount of times that there are bits. We want to make sure that we get through the whole thing so we circle around the whole time. And the way we're going to do that is by using a loop counter. So we'll just call this loop counter. And so let's do the things that we know we have to do in the loop. We know that we have to shift both registers in order to move the top bit to our working number. And so we're going to shift the high number first. And we're going to do that with a logical shift left with an S suffix, the high, which is R5, and we're going to shift it by 1. And I'll explain this in 1 second. When we do a left shift with the S suffix, the S suffix tells the processor, please update the CPSR with the result of this operation. More specifically, when we do a left shift, if we have a 1 in the most significant bit, when that gets shifted off, it'll put it in the carry flag in the CPSR. And so now if a 1 got shifted off, it's in the CPSR. And what we can do is we can add this to the working number to put it in the least significant bit. And so we'll use the instruction ADC to our working number, R6, and we're going to put 0. And what the add carry instruction does is it adds the number that's given plus the carry flag if it's there. And so it's there for situations like this where you have some kind of carry and you're moving to a higher set of bits. It allows you to add that overflow or that carry if you need it. And so this is perfect for what we're doing. The next thing that we need to do is we need to shift the lower 32 bits. And so we're going to do the same command, LSL, on the low, so R4, and we're going to shift it by 1 again. And then we're going to use the add carry again, but this time we're going to add it to the higher 32 bits. And what we're going to do is, if you can visualize it, we take the lower 32 bits, shift it left by 1, and now if there was a 1 there in the most significant bit, it's in the carry flag. And what we wanted to do is these two registers act as one giant number. And so we want to add that carry to the least significant bit of the higher 32 bits in order to make it act as one giant number. And so we'll do add carry to R5, which is the high. And again, 0, because we just want to add the carry flag. And so that takes care of our actual shifting. The other thing that we have to do is we also have to shift the working number every time as well. And we need to do this prior to shifting our registers so that when we shift something off the top, we can just add it to the working number. And so we'll put this before the high shift so that it happens before that. And we don't need to update the CPSR for this. We just need to shift it. And so if you compare this to the video that Ben Eater made, we have to shift everything. We have to shift the working number, and we also have to shift this one giant number, this one giant 64-bit number. But because it's in 2 registers, we have to do it in more steps. We can't just shift it once and be done with it. We have to actually do a good amount to shift everything over. That is the big shifting part. We can put here shifting numbers. What else do we need to do? Well, after it's shifted, we need to compare what's in the working number to 10. And if there is a 1, we need to add it back to the lower 32 so that when it gets shifted over all 64 bits, it's in the right place at the end. And so after this, we're going to compare, let's label this, so what we're going to do is we're going to compare the working number, which is an R6, to 10. And if it's less than 10, we don't need to do anything. If it's less than 10, we just want to shift everything over again. So we'll do branch if less than 10, and we'll go back to loop. However, if it's greater than 10, we need to subtract 10 from that. So this is the else, essentially, if not less than. We're going to subtract from R6 10. And then we're going to add 1 to the lower 32 bits of the 64-bit number. And then go back to loop. And so this is, for the most part, what our loop is actually going to be. We need to add an exit condition out of this. But this is how we're going to determine everyone. After we do this 64 times, that remainder is what we're going to write to the output memory. And so let's actually work on this. So the loop counter is going to be in R9. We need to create some kind of initialization zone prior to the loop so that we can reset this counter. So I usually use outer, as in like outside, and then we'll move into R9, the number 0. And then up here, before we start shifting numbers, we'll add 1 to R9. And then we have to actually make the condition that checks to see if we want to keep doing the loop or we want to leave it. And so what we're going to do is we're going to compare R9 to the number of bits that we're processing, which is 64. And since this is not 0 index, so this is going to essentially be a 1 to 64, actually counting the bits, we want to branch if it's greater than. And we need to come up with some name of the section where we're going to store the number to memory. So let's just use store. That seems easy enough. And we'll put this down here underneath the loop. So far, what our program does is it has a counter. It multiplies 2 numbers together. it saves it into two registers as one giant 64-bit number. It loads the output and it saves a line ending. And then it starts, it's the long division. It goes through all 64 bits. It rotates it off one by one. It left shifts it one by one. And every time the left shift happens, we check if that number that's created by doing the left shift into the working number is 10 or greater than. If it's less than 10, we shift again. But if it's greater than 10 or equal to 10, then we subtract 10 out of that number and we add one to the lower 32 bits. And what that will do is as it shifts over, it'll give us the next number that we want to process. After that 64 bits happens, though, we'll have a number in our working number. If it's 0, then it's 0, but it's going to be something. It can't not be anything. And that is the number that we want to store in the output. And so in the store section, we want to add, we'll use R7. So if we come up here, we already did the number to write. It's like I have this written down in front of me. We're going to add to the 0 ASCII value, like we did with the other integer to ASCII. And we're going to store that in R7. So R6 is where our working number is at, and we're going to add it to the ASCII of 0. And then what we need to do is we need to store this into the output. Our output string's in R8, yep, correct. And then again, we're going to decrement this. And then we want to branch up to our initialization section again. So right now we have something that will process all the numbers. It'll go through 64, it'll save the remainder, it'll print it out, it'll go again, it'll go again, it'll go again. However, we need to make sure that it knows when to stop, or it's going to go again, go again, go again forever. And so we should put this in the initialization section up here. But how many times does it need to go? Does it need to go 1 time, 5 times, 10 times? It depends. There's a couple of things we can do. We can check to see if it's 0. We can check to see if there's anything else to write. We can check a couple of different things. I know, and this is how I wrote the program, that we're going to need all 20 digits. And even if you wrote this to always do 20 digits, you would be fine because it would just do zeros. They may be useless zeros at the front of the number that mean nothing, but they'll still be zeros. And so let's add another counter here for the number of digits that we have. Oh, digit. And let's work with that. We need to first initialize this value. Again, we don't need to, but again, I like seeing it. And we'll put in R10 0. And so in the outer loop, the first thing that we should do is see if we need a break, because if we need a break, then we don't need to reset the inner counter. And so we're going to add 1 to the outer counter. And we're going to compare this to 20, which is the max number of digits. And if it's greater than 20, then we want to actually write the number to output. We want to write everything that we stored. Again, we want to use greater than here because this actually turns it into, it's a 1 indexed counter, not a 0 indexed. We're calling our first digit 1 and not 0. And so we'll just call it right because that seems to go well with what we're doing. But we still need to do one other thing. We initialize the counter here, but we also need to initialize that remainder. If we don't set that remainder back to 0, what will happen is that we're going to get all kinds of crazy things happening. And so before or after you initialize the counter here, you also need to reinitialize the working number, which is R6. And so we're getting really close. Right now, what the program will do, and we can walk through this a little bit, is that it multiplies the two numbers, it stores the two numbers in the two different 32-bit registers. We go to the end of the memory here in line 24, we write the line ending because we're going to be writing this backwards. Then we store it and we decrement the address. We initialize the counter of the number of digits that we want to do, which is 20. And now what we do is we do the comparison to see if we need to write more digits or not. If not, we go to the right. But if we do, we initialize the variables we need for our loop. We then see how many bits we've moved. If we've moved all 64, then we get out of it. But if not, we shift the higher 32 bits. We shift the lower 32 bits. I'm sorry, we shift the working number, the higher 32 bits, and then the lower 32 bits. Then we check the working number and see if it's 10 or greater than. If it's less than 10, we just shift all the bits again. If it's 10 or greater, then we subtract 10 and we add 1 to the lower 32 bits so that when it shifts over, it gives us the correct number to work with the next time that we do this huge loop. After we do the 64 shifts, we take the remainder, we add it to the ASCII value of 0, and what it gives us is the number that we want to store in a memory. We store it in memory, we decrement the memory, and we do this 20 times so that we get the 20 digits. After all of that, all we really need to do is write the number to the output. So we'll do setup right here. The first thing that we want to do is obviously put the supervisor call here, which is 4. Our first parameter is the file descriptor, and for this it's going to be 1 because 1 is the special standard out. The next thing we need to do is load the output into register 1. Output address, and the last one is the length. And this is always going to be 21, so we don't have to use our null right. And then do the software interrupt with SVC 0. And now all we have to do is exit the program. Again, we're going to move into register 7, number 1 for exit. Our error code will be 0. There is no error. And then do the software interrupt. And so even though this concept is kind of abstract, and you really need to live with this idea for a while before, or at least I did. I had to live with it for a while before I finally understood it. But really, this whole program is only about 30 lines of code. And theoretically, you could take this 30 lines of code and you could cut it down to about half that if you're working with a 32-bit space. But you can do all kinds of things now, like divide out numbers to X amount of digits, or calculate whatever you want like that by using long division in binary. So let's run this and make sure that it actually runs. It's kind of cool to see the code, but it's even cooler if it works. So we'll do make, and we're going to run the main. And we get a 111-074-004-887 657-99040, and that's our expected output. And again, this is probably the hardest one that you're going to do. The next couple of exercises are really just introduction exercises to things that this series doesn't really go in depth to. So if you made it through this and you understood it, congratulations. You're definitely on your way to being able to really work with this language and really think at this level. And if you haven't gotten it, watch videos, watch the Ben Eater videos, see if you can internalize that. And then after that, see if you can close your eyes and visualize that in your head, and then come back to this one. You don't have to understand it the first time. There's no rule that says that when you do programming, you have to understand anything the first time. If that were true, there would be a lot of people that had nothing in their lives because they give up after the first time. You can do it. It just takes time.